John Conway's Game of Life deals with a cellular automaton invented by mathematician John Conway at Cambridge University. It consists of a collection of cells which, based on a few mathematical rules, can live, die, or multiply. Depending on the initial conditions, the cells form patterns throughout the course of the game. Let's take a look at the basic rules. In each block of cells, there are some cells that are shaded, living cells, and some that are not, dead cells. Every generation that the block of cells goes through results in a different formation of these dead and living cells. In order to tell what will happen with living cells, you look at the neighbors, both adjacent and diagonal to the cell. If 2 or 3 of these neighbors are living or shaded cells, then that living cell remains a living cell in the next generation. On the contrary, looking at the dead cells in the next generation, if a dead cell has 3 living neighbors next to it, it will become activated in the next round, becoming a shaded or a living cell. If it has any other number of living cells surrounding it, or no living cells surrounding it, it remains dead in the next generation. After a generation has passed, there are 3 types of cell structures that are possible. The first are known as still lives, sometimes referred to as stable patterns. The second, oscillators, also referred to as periodic patterns. And the third are spaceships, which can include both migratory patterns and population explosions. First, we'll take a look at still lives. Still lives are patterns that, after any number of generations, will remain in the exact same cell structure that they started with, having no new cells produced or no living cells killed. The following are some common structures of still lives: the block, the biblock, the beehive, and the honey farm. We also have the loaf, the bi-loaf, and the bakery. Also on the bottom are the tub, the barge, the long barge, etc., which continuously gets longer as 2 more cells are added to the bottom of the formation. Similar to those are the boat and longboat, and the ship and the longship. Some other unique patterns include boat ties and ship ties, as well as other smaller patterns such as the canoe, the aircraft carrier, the integral sign, the mango, the pond, and the snake. Each of these cell formations will not be altered in any way with each generation to come. Next, we will look at oscillators. Oscillators are cell structures that after a number of generations will return to the starting pattern that they started with. These generations can be as little as 2 or as high as 312. Some of the smaller cell oscillators are shown here, such as the blinker and the toad structure. However, as we can see, oscillators can involve more generations before returning to their original pattern, such as the pulsar with 3 generations, the cross, also with 3 generations, and lastly the star with 3 generations as well. There are more examples, however, of structures that include more than 3 generations to return to their starting pattern. The clock is a common 4-generation oscillating pattern. And the octagon takes 5. An 8-generation oscillating pattern can be found in the galaxy structure. This structure is known as the tumbler and takes 14 generations before returning to its original starting position. Starting out as a row of 10 blocks, this structure quickly evolves into the 15-generation oscillator known as the pentadecathlon. We'll see it here first in slow motion, and then we'll speed up the generations to show you what it's like at a quicker generation rate. The third result of cell generation is spaceships. Spaceships are generation results that will move the cell structure across the plane of cells. Some are in all directions, known as a population explosion, and others will simply move it in one direction. This one-direction motion is known as a migratory pattern, and the spaceship structure is an example of this. An example of a population explosion is seen in the cell structure known as the explosion. Note that the cell structure moves across the cell plane, expanding in all directions. Most spaceships will eventually cease moving across the cell plane and become stabilized in the form of still lives and oscillators, some of the remaining cells destroying themselves through underpopulation or overpopulation. Note how this explosion cell structure eventually becomes stable by producing 4 oscillators, the 3-generation repeating pulsar oscillators. The cell structure known as a small explosion is very similar. Instead of an oscillation pulsar formation, this cell structure ends in a beehive. This brings us to Methuselah structures. A Methuselah is a pattern that takes a large number of generations in order to stabilize and becomes much larger than its initial configuration at some point during its evolution. However, Methuselahs are patterns that do not go on forever. Their exact definition is not completely agreed upon by all mathematicians, but most definitions place restrictions on the number of cells allowed in the initial pattern. Mathematician Martin Gardner defines Methuselahs as patterns of fewer than 10 cells that take longer than 50 generations to stabilize. Some of the most common Methuselahs include the F pentamino, diehard, and the acorn. The acorn is a pattern of 7 live cells developed by Charles Quarterman. This cell structure takes 5,206 generations to stabilize and produces a 633 cell pattern referred to as its oak. Another example of spaceships are gliders. Gliders move diagonally across the cell plane. They're important because they can be easily produced and can collide with other structures to form complicated objects. The best example of this is the formation of a Gosper glider gun. This formation is very important because it disproved John Conway's theory that no structure could infinitely produce cells. The Gosper glider gun is just one example of a structure that John Conway did not think was able to exist in his game of life. There's no reason why you can't be the person to discover the next new fascinating feature of the game of life that no one has thought of yet. So get on your computers or grab some graphing paper and start creating.